All right, so first of all, thanks to the organizers and thanks to our wonderful colleagues for 30 years of fun. I'm Justin. I'll wait for you here. It'll be wild. But I'm going to be talking about some work that was done in collaboration with Lev and some of our colleagues in Hefei, China. In fact, most of the actual work was done by this crew. Unfortunately, I don't have good photos of everybody in that team, but you should keep in mind that they're the real heroes of this story. But this is building on what Lev was talking about earlier. So I want to go back and recap a little bit, at least my understanding of Lev's understanding, of Avi's understanding, of Kira's understanding of what's going on. So hopefully I can help disambiguate what everyone's actually saying about this. So as a recap, so this all came from interaction-free measurement. Let's see if I can get rid of that thing. Where we have an interferometer that's tuned so that all the light comes out of one side. And so if there's nothing in this arm, then this detector you place in the dark port over here never clicks. And whoever is watching that detector is sad because they get no information, no one's talking to them, they're all alone. Lev is very happy about this case because there are many paths, he likes many worlds, this requires many worlds, and so he's very happy. But then Avi comes and spoils the party. He puts a bomb over here. Now the light spoils this interference and it can come out and the dark port detector clicks 25% of the time. Person who got that photon is very happy, or got that click, he got some information. Lev is sad because now it's all one path. So what's going on here? What it looks like by putting this object here, Avi has changed the possible futures of what clicks are going to happen here. Which, if you're talking about coherent light, this isn't so interesting because you say, well, the light's going both directions. Of course, if this light never reaches there, I don't get interference, then of course I change the future. But if I'm talking about a single photon coming through, now it's stranger because somehow absorbing over here or preventing it from passing over here means it had to go down this path in order to reach the detector, but then how did it know that happened? And so it seems to be a non-local type of thing happening here. So if you go back to Bohr and say, okay, what did Bohr say about this? Probably. He'd say something like, well, the source emits this forward green wave here. The shutter, placing it here, will disturb the configuration holistically. This means that the wave here is encoding the likelihoods holistically. It does not describe the local reality for each trial, and you should not even try to think about how the random trials actually happen, how this click happens. But because you disturb the configuration, you disturb the likelihoods, and of course you're going to get that. So that's Bohr. Now Lev, my understanding of Lev version 1.0 in this world D, where this detector clicks, he says the source emits forward wave, this is this green wave, and it does its thing. The detector also sort of emits a backwards wave, this red wave, and the reality is where they overlap. Now, there is no particle here because everything is the wave function. So that all that matters is that these two different forward and backward waves overlap, and that's the reality is where they overlap. Now, this requires two things. It requires the shutter here. When I place it here, it blocks both waves. So the forward wave does not pass. The backward wave also does not pass. Then you don't get any overlap in this case. The other thing you need is that this click, implicitly, because it has this backward wave propagation, is retrocausally affecting the past trajectory in order to determine the reality. Implicit to this picture is a retrocausal interpretation of how reality is along this path. This is Lev version 1.0. Now, Avi says, well, I don't quite understand this. You say reality is over here, but if everything is waves, everything's the wave function, I see green waves coming here, I see red waves here, so isn't reality still partly there? You still have waves there. And this is very negative attitudes. This is a negative Avi, if you like. So Lev clarifies. He says, no, Reality is local. Locality is very important, like a particle, but it only exists where the two retarded and advanced waves overlap each other in this extended space-time region. The other waves, this green and red, that don't overlap, do interact with other bits of reality because they bounce off of mirrors, they get blocked by the shutter, but they are not reality themselves, despite being part of the wave function, which is the only reality. There's nothing else but the wave function. So Lev has very clearly fixed the confusion here. But Avi says, I'll go work on a different interpretation. Okay, so what does Yakir think about all this? He sees Lev, wave function is everything. Yakir said, Yakir says, no. Only particles are detectable. As particles have localized mass and localized charge and localized spin, you can't just suddenly move them somewhere else. They have to be local. So by conservation laws, there can't be many worlds. There can't be a wave function collapse that move these things around. There has to be some local coherent story I can tell about how this reality evolves to get the results that we see. So to actually understand what's happening, we need to look at the dynamics of the measurable properties, not the kinematics of where these waves live, but the actual dynamics. And that's where this particle will live. That's how we'll understand how the particle properties evolve. Dynamics are non-local in space. And they're determined by both past and future boundary conditions. But they have uncertainty if I only look in the present. And that uncertainty protects causality, so I can't predict the future, even though I have this future boundary condition. So I think here that is correct. Excellent. So this is Yakir. He is unique. He is following his own destiny. So Yakir elaborates. So see, there are non-local equations of motion for these properties. So this means that the particle actually moves along some local path, but it's non-locally aware of the shutter over here remotely. So it's still local, but it can still be influenced by this thing over here. And there is no wave function. The wave function is kind of a red herring, if you like. It's just encoding these boundary condition information. Very different picture. Of course, Lev says this is heresy. Everything's the wave function. It's all, there's no particles. This is nonsense. So of course, our experimental colleagues are just getting fed up with this argument. And they say, I don't know what you're talking about. What are you arguing about? A relevant definition is much simpler than this. Reality is what we can verify in the lab. It's what we can see in experiment. Everything else, it's just words and math. And of course, they're talking in the lab frame, and then they have fun there. So there's no Lev, now he thinks about this, he becomes Lev version 2.0. There are many versions of Lev, but we now have a modified understanding. So he says, no, there's no problem with experiment, because if we place probes in space that weakly interact with these passing waves, they will register a small trace wherever that localized wave actually went. But the interaction must be weak to not disturb the rest of the setup. And this is just like a test charge in freshman electromagnetism. If I want to know what is the electric field or what is the magnetic field, I put a very tiny test charge there and pick the limit that charge goes to 0. They don't disturb what it is that I'm trying to determine. So it's exactly like this. And he says that the traces of these weak probes that you put will be found exactly where the forward and backward waves overlap, which confirms his earlier statement that this is what reality is. This is what will affect these probes very weakly. And these local waves will have, usually have an environment that they're traveling through, and they'll always weakly interact with this environment. And so you expect these small traces to be just accumulating in the environment wherever the wave goes. And that's where you know where reality is. That correct, Lev, for Lev 2.0? Good. So Yakir says, well, this makes sense. If we weakly measure things in a post-selected setup, then what the weak probes will see are the weak values of the particle properties. And that will indeed reveal kind of what's going on, where things have been. there's an agreement here. Interpretation is very different. It's particles or waves, but the agreement is that these weak probes should give you the right answer. So a weak measurement experiment should give results consistent with both of these pictures, either this retrocausal wave dynamical picture or this kind of non-local particle dynamical picture. And the point is that a particle will leave no first order trace along the shutter path at all in either interpretation. So in some sense, it wasn't here. So now to just give a little bit of math that connects these two pictures, and so why is a weak value showing up here as a trace? We can imagine if we just prepare some initial configuration, then we do some weak coupling, some sort of weak unitary coupling with some probe that couples to some property of the particle pi, like a local projector, or it's some property of the particle. And then we do a post-selection later on. Then we can describe all this with the amplitude, right? Initial state, my weak coupling, my post-selection. And if I just factor this, I can see that I have my original amplitude before I did this weak coupling, multiplied by this thing, which is a weak value of a modular variable. And so this is a modular value that completely determines what this small little weak coupling is going to be. I can expand this exponential, and this turns into a series of sum over all these nth order weak values that are parameterized by this coupling parameter epsilon. And then I say, oh, well, when epsilon is sufficiently small, then epsilon squared and all the higher order powers are essentially negligible, and I get down to this linear order effect that's completely determined by the weak value of whatever the particle property is. And that is going to be exactly the small trace that affects the wave itself. So the weak value and the small trace in the environment are going to be the same thing. They'll give you the same information. Okay, so with this preamble about what we mean by things being there or not, now Lev and Avi notice something interesting, which is that if they go back to their original setup, Avi can place this shutter here, and he seems to be non-locally sending the information that he placed the shutter here to Lev down here. But there's no carrier there. You can say, well, there's no way if I put a weak probe here, I'm going to see any way for this information that I put this shutter here to arrive at this detector. This is kind of funny. So Lev is communicating to Lev by saying, Avi is communicating to Lev saying, I put this shutter here. He gets this click saying, oh, I see Avi put this shutter here, but there's no particle here to carry that information. So from Yakir's perspective, this is a non-local thing. So this carrier knew about the shutter and then informs Avi. But locally, it never interacted with the shutter. Now, as long as I put a probe here, where this epsilon squared is below whatever noise floor there is on whatever probe I'm trying to do, then this information is going to be transferred without any apparent barriers at all. So I can experimentally verify this fact. But with this original setup, when Avi does not use the shutters on this left side here, then there is going to be a trace that you can measure here in Lev's sense of a trace, which means if I make an experiment and I check was there an effect here, yes, I'm going to see it. This is an asymmetric case where I sort of get half a bit that I can transfer without the carriers, but the other half of the bit, I will see carriers in that channel.
I mean, you could encode the bit on whether there's a carrier.
Sort of.
I mean, something being there or something not being there, that's a bit of information. So
if you can make the assumption that I know that it wasn't there. So it's a little bit subtle, but there's a way to patch this up so I don't have to make this subtlety. And this is what Yakir and Lev came up with a couple of years ago, is they just extend this idea by kind of adding this doubly nested interferometer inside. And then you say, if you block the shutter on both places now, this will work exactly like before. So I'm going to get a trace that only follows this outer path. So that's where any weak probe is going to see that there are carriers. And anywhere in these internal areas, I won't see any carriers. So putting the shutter there, it doesn't seem like I have anything to carry the information locally from here to there. But now in this double setup, if I don't put anything here, this interferometer is tuned so that all the light is just kind of lost out here and never makes it back to this other path. And so I'm going to get a click at this other detector here in that case. So now if I do nothing here, then I will definitely get a click over here. If I do something here, then I definitely won't get a click over here, and I can just put another detector over here. So now I have a nice distinguishable case where I can get a click when the shutter's there, and I can get a different click when the shutter's not there. So I have confirmation on both halves of my bit, as opposed to half a confirmation, then assuming that the other thing was true. The weakness here is that you have some loss. So this is going to fail some fraction of the time. As Lev pointed out, there are ways that you can improve this, but even just this variation is interesting. So the experiment that I'm talking about implements exactly this protocol and says, well, let's do that. Let's put all these weak probes in and see does this actually work as anticipated. And again, our colleagues in Hefei did some amazing work here. I'll try to unpack how this works. So here's a quick summary again. So Avi has the control of this shutter, and we say, well, let's call him Bob, and let's put him in this region over here, and let's block off some gap here that we're going to call transmission channel. So that anything that crosses this gap, in principle, some eavesdropper could put a probe there and say, is there any carrier that's crossing over the gap between Avi and Lev here? We put Lev over here, and he has control over both of these detectors. So he just says, does detector 1 click or does detector 0 click? He'll get either bit value, or it's lost and he gets none. Now, in practice, it's easier to, rather than cascade them like this, to fold them over this line. So if you just imagine a horizontal line here and you just fold the top over the bottom, then you can fold everything into one kind of nested interferometer, and that's the setup you have here. So now this inner interferometer here is both this one and that one. And then this path here that bounces and it comes back is going to be this path bouncing off that and then coming back. So we folded it so that the bit 0 case does this and the bit 1 case does this. So bit 0, you have the laser come in, and the trace you'll find along this path that goes up here, bounces off, comes back, and then you'll see a click down here. For the bit 1, where Avi puts a block, now you're going to get a trace that goes up here and bounces off the wall and comes back down here again, and then ends up with a click here. But in neither case, if this D1 won't fire here, D0 won't fire here, but I may have loss elsewhere. Now, of course, in experiment, there are details. So I wanted to comment on the details. So the way they actually do this is that they take a pump laser and they put it through a double etalon to make it a very, very narrow frequency band coming in. This frequency band, narrow frequency laser goes into this nested setup here. The setup actually is tuned with a separate laser here, this blue laser, and that just goes through and helps mode lock the whole interferometer. And there you have little piezo controls to make sure that the interferometer stays mode locked. So this is just helping everything stay aligned very precisely. But they frequency filter out the blue laser so that it doesn't affect the rest of the experiment. It just gets everything locked. Now, the reason that they set up a very, very narrow frequency band here is that they want to put probes in each of these arms and learn kind of where the photon has gone. So they put these electric optical modulators here that will kind of dither the frequency a little bit and create sidebands. And they put different dithering frequencies in each of these arms so that they can spectrally filter it and learn which sidebands appeared. And that'll tell you where the photon was, because it gets those sidebands if it went through that modulator. It doesn't get the sidebands if it doesn't. But these are kept very small, so it's still in kind of the weak coupling criterion. And then now they can put the block here, or they can take the block out, and then see which of the detectors, D0 or D1, click, or if neither detectors click, it's lost. Well, how do you determine this? Well, what they do is they take this pump, they put it through a periodically pulled KTP crystal, which creates a down conversion pair of opposite polarization. So then they split the two of the pair so that one becomes an idler that's acting as a herald that triggers the detection for the signal photon. So when they look at coincidences between the trigger and either D0 or D1 firing, then they know, yes, a photon got there and which value it got. Every time you don't get a detection, it's lost somewhere and it's inefficient. That's how they implemented it. Now, what's cool about this is because they had both of these bits, they could actually send real information. So to make this point, they took a QR code and made it just a pixelized array. So they did a raster scan linear line by line array into 21,025 bits. Each of these is either black or white. So each pixel is an independent bit that you can send. And then they just one by one, and I think each bin took 1,000 seconds for them to integrate it carefully. So this is a really long process together. Bin by bin, they just waited until they got the first successful heralded click, and then said, okay, that's the click we got. They could, of course, have done better than this. They could have redundantly encoded the bit and all that and eliminated the errors, but this is just kind of the raw error before you do anything fancy. And they got error rates of 2.3% for bit values of 1 and 10% for bit values of 0, which just visually looks something like that, which you can still see. And if you scan this with your cell phone, this QR code will go to the web page of the experimental laboratory, which is kind of fun. So it works. Now we have a case where you can send both bit values. But now the question is there a trace?
Can you go back for just a second?
It doesn't actually go to the website, it gives you the text.
Oh, it gives you the text.
That's how it works. So
Yeah.
one on the red sufficient.
Yeah, it works. We got information, communicated information. But did we communicate it with a trace? So now let's look at what did all these acousto-optical modulators tell us. So here's the kind of the spectrally filtered counts. Bin. So first they just calibrate what these sideband amplitudes are, so they can see what the reference sidebands are. So they tune the interferometer in a way that they can see all the sidebands. And then after they calibrate the amplitudes correctly, then they tune the interferometer back to the way it should be. And now they do the experiment with bit 0 and bit 1. And if you look here, for bit 1, which is on the right here, what you expect from this like overlapping path, this trace where Lev says we should find a trace, what we should see is a signal in C and E. And if you look carefully, if I follow a photon through this path, it'll bounce, go through B once, go through F once, go back through F, go back through B, and then click. So I expect 2 instances of going through B and 2 instances of F. And so if I look at bit 1, well, B actually does have double the amplitude it should. It goes through twice. F does have double the amplitude it should. And then we see a signal in E, just as we expected. But A, which is in the transmission channel, is missing. So there is no signal in A. So according to just our weak probe that we put here, there was no probe that was here to this linear order in the interaction. Now, bit 0, which is the case here, what you expect is that I went here, it goes through C, comes back out, goes through C, and then comes back out. And so C gets a signal. A still has nothing. So this matches exactly what Lev and Yakir predicted. That there is no weak trace in A. The weak value here is 0, so the first order effect vanishes. And the second order effect is below the noise floor, so you can't see it. So everything works. So is this the end? To be determined, but at least congratulations for everybody for 30 years of not interacting.
That crystal clear, yeah. Any questions?
They settled the issue for you.
That's right.
The next, yeah. I want to say something about Len's idea for traces. If you have, for example, a trace that an electron leaves, he wouldn't mind if this trace will be only magnetic field, no charge, no electric field, no gravitational field. He will still say there is an electron there, that's a trace, but for some reason he decided not to leave a trace of charge, electric field, not to leave a trace of magnetic field, only to leave a trace of of magnetic field, not electric field, no gravitational field. In my picture, where there are pairs of particles, positive and negative, then I know exactly what traces are there, because I calculate the addition of the two. So the picture of just saying there is a single electron, even when you have negative traces, etc., then it's only worried that there will be something there, not worrying what will be there. And in my picture of discovering a situation where you have negative potential operator, you have known that the single particle moving, that gives you really good information what traces there are. That's the difference.
This is a good point. Yeah, with the actual observables, you have a much more fine-grained way of asking questions. This particular property, this pair of properties.
So in the place where you see the first order zero information, I would say there was moving there a pair of photons with positive and negative energy together. There is no energy, there might simply polarization moving there without energy. So the whole modification with polarization takes that when you see 0% of photon and only polarization moving there, and this way you can collect information by the polarization without any photon moving. That's an interesting modification.
Yeah, interesting. And I also like in your picture, kind of what's kept constant. So if I just go back to a simple interferometer, when you say that I have one photon coming in, I think it's clear in your picture what you mean is that the total number is one.
Yeah.
You don't say that it has to be a fixed one only. You can have multiple things as long as the total.
Kind of variation where the real negative and positive projection with values, they reach phenomena with nothing moving there according to the usual rule.
Good.
So what would the implications be if you're able to eventually lower the noise floor and measure something that like, I guess I'm just wondering what's the interpretation of that in terms of this trace? Like just that that's the weak trace and that hurts the weaker.
Yeah, so one of the possible answers to that question is that when you introduce a perturbation, like something like this, then you expect just by introducing the perturbation, you're going to affect the tuning of the interferometer. So you expect clicks to appear in weird ways just because I introduced the perturbation. So by keeping it only to first order, what you're doing is saying I'm neglecting the source of the perturbation causing what I see, and I'm trying to look at sort of what was there before I added the perturbations, is the theory. Now, of course, this can fail occasionally, which is what happens to Dove prism, is that you end up with an amplification that removes a factor of epsilon, and so it actually boosts a second order epsilon effect to become visible at first order epsilon, and then it's unclear, like, was this a disturbance effect that was amplified, or was this an intrinsic thing that wasn't a disturbance effect? So by going to second order epsilon, now you introduce an ambiguity. Are you talking about the actual disturbance to the system, or are you talking about something that was there before you disturbed the system? But when you lower the noise floor and get more and more sensitive, then you're going to pick up these higher order terms, and then you have to grapple with that question: is how seriously should we take them? Because no matter what you do to try to probe, you will disturb it somehow, and you don't want to misinterpret the signal in some sense.
This is maybe a much more practical question. So is there any advantage at all doing actually communication as opposed to whatever.
In this setup, clearly not, because there is an enormous amount of loss. They had to wait a very long time. This is a
Even
very.
if there were no loss, or even if the time, the latency weren't an issue, is there any advantage at all in terms of being more robust to channel noise or dephasing or?
My naive feeling is no, just because a lot of this depends on very sensitive interference cancellation to get these kind of effects. And so any environmental like agent who comes in and wants to disrupt your communication, even if they don't see carrots, they can just like blast it with a huge field and ruin your day. It's not necessarily practical, but I think it's interesting. Love may disagree, maybe you know practical use.
It's not practical, but conceptual. If Eve kind of decided that during the communication she does nothing, and she comes later and look on the channels and try to get information. If it's really this kind of counterfactual interaction free, she will not find any information. Of course, why Eve should not be active? If Eve is active, then this kind of communication is
You mean looking for a trace or something like that? That's what you mean by
Yeah.
finding information.
Yes. So then, really, and there will be no trace, especially, and there is interesting thing that we can make key, secret key only with when we look for a shutter and not for empty shutter. Empty shutter is problematic because this first order, second order is there, and it's problematic. For shutter, in principle, there is no any order. So if you have zero information. So in principle, we can distribute secret key between Alice and Bob, such that passive if will get zero information. And this is kind of strange. I think this is one of the most desired properties of this interaction restore, that you can distribute secret path without kind of crossing, without moving anything in the chat.
Yeah. So if you have a very artificial setup, so if you know Eve is in this one location and she can only do a very weak probe, then you can get stuff by her without her noticing it happening. This is very specific situation.
No, there is a boundary in Alice, and there is some space between Alice and Bob. And Eve can do whatever she wants there, but late.
Yeah, but if she tries to strongly measure, it'll just ruin everything.
She can ruin the communication, of course, but this is.
That's my point. She can just ruin it. All right, I suppose I should stop for.
Okay, thank you, Justin.